Can everyone see here? It's fine. Okay. Okay, so we'll just do a brief recap of what we. So we basically talked about the random walk and so on the infinite line. And then we considered various cases like, so we considered these three cases where either both time and okay, and so then we wrote basically we looked at some properties of the random walk, and so we looked at so we defined the general random walk where you move with probability p to the right, q to the left, and you don't do anything with some probability. And then we calculate things like what is the average x, and then what are the fluctuations in x. And then we asked what is the probability, full probability distribution, and what is the equation determining it. And then we also looked at the okay, so we looked at the case where the time is continuous, and finally we looked at the case where both are continuous, and then this is at probability density. So in this case it's probabilities and these are densities. Okay, and so basically we then tried to connect all these things. And so one of the things was if you have an unbiased random walk, in that case, in the discrete case, basically, after some time, if you ask what is the probability the particle is at various points, then you get some, so you get some curve like that, like you. So this is the probability of if you have a discrete lattice, then this is the probability that the particle can be at various sites. And then, of course, if you can imagine that you're looking at a scale where you can't see the distance between these sites. Okay, so you just imagine that the spacing between the lattice sites is really, really small. So then, of course, it gets more and more dense. Okay, and then you can ask, so going to the continuum limit basically means like now the particle, the lattice spacing is so small that when you look at it, you just see, you do some coarse-grained thing, right? So then you can ask basically, what is the total probability in some distance dx? Right, so in some distance dx, there's already a lot of lattice sites, and to find the probability, so then what you define is Ex dx is the total probability that it's in this region, right? So you have to sum all these probabilities, and that will be like summing over all sites which are for which xa is between x and x plus dx. So you sum all the probabilities, and then so that's how you get a probability density. So basically, going to the continuum limit means doing some coarse graining, and here you are doing coarse graining both in space and time. And, so in that case, of course, you get some continuous distribution, right, which looks like the Gaussian. Okay, so this exercise you should do, like going from the binomial distribution to the Gaussian. It's some limiting procedure which one should understand properly. Okay, so Okay, so then after that, what we wrote these equations and we first solved them on the infinite line, and then we discussed trying to solve them in the on a finite lattice, right? And then we also discussed something about master equations and all. Okay, so one question that there was yesterday was, if you have this equation. Okay, can this be solved by someone asked, right? You asked, I think. So did you try to solve it? Okay, I mean, okay, if you, I mean, you should try to, I mean, if you have a question, it's better you do it, right? I mean, okay, so because it's not, you just take Fourier transforms, right? So what do you get if you take, did anyone think about it? No. Yeah. Yeah, so but will you be able to get the solution? So if you take Fourier transform, of course, what, I mean, naively it seems what you'll get is I omega p tilde k omega is equal to minus d omega, right? This is what, naively, this is what it looks like, right? But this doesn't give anything, right? I mean, you can't do anything with this. Okay, so it's not clear we can do. But let me just mention that something that you can that you can do it in a slightly different way. So here the point is that we are solving an initial value problem, right, in time. So x, so this is the initial condition. And so, I mean, so one way to solve this, where you can take this initial condition into account, is actually to not do a Fourier transform, but do a Laplace transform. Okay, because then you can start from, you can put some information about time t equal to 0. Okay, so that's one way to do it. The other point that maybe is useful to note is that, okay, so supposing so yesterday we solved this equation and just taking Fourier transform in space, right? And then we got the solution that E of xt is equal to what? dt. Okay, so now supposing you define this object, I call so it's gxt, which is basically this this solution. Okay, so this is a special solution for a particular initial condition, right? So I take this special solution and multiply it by theta of t. Okay, so this solution, of course, is valid for t greater than 0, right? Because for t less than 0, it doesn't make sense. So only for positive times, it makes sense, right? So supposing I define what I call a Green's function, such that for positive times, it's exactly this, and for negative times, it's 0. Okay. So then if I ask what is the equation satisfied by G, then it's del Tg is equal to, so I can take del Tp. So there will be two terms when I take a time derivative. One is del Tp, which gives me this. So that's d del x square p into theta. So that's again G. And then there's a term which is, so what is del T of theta function? Delta function. So delta function, and but at time t equal to 0, this is a delta function, right? So this will give plus delta x delta t. Okay, so now I mean this equation actually you can solve by Fourier transforms. Okay, so this equation, if you take Fourier transforms in both space and time, then now you get something like, so I define G. Plus, doesn't matter. You're asking how I got this? Which one? No, which equation is general? This one. Right, this is, so this equation, no, what is your question, say again? Right, so given that G is defined as this, so here P is this object. So then I'm saying, like, if you take del Tg, you get a delta function into P of xt, but since delta function means T is 0, so if you put T 0 here, you automatically get delta function, right? So that's why you get a delta function. Okay, so you define this, and then if you put here, so basically you then get I omega G tilde uh, equals to minus d k square G tilde plus 1. Right, so this gives you that G tilde k omega. So, I mean, this form, sometimes you might see it in places, but so what this really means is that it's this solution, okay. So this, of course, you can also, since g of xt is this, if you directly take a Fourier Laplace transform, this is what you'll get, right? So that you can also see with, while solving this, we had actually earlier seen that g tilde of kt is e to the power minus d k square t, and then this theta t is there. And now if you take a Fourier transform in time, so then of course you will get exactly this, right? So it's basically this object is the, but then when you take the Fourier transform, you have to remember that on one side it's really 0. Okay, so now we'll discuss a bit this. I think so. I think some people were confused about this finite system. So let's do that again. So let's say we have this lattice. So yesterday I wrote this thing, and so we were discussing this random walk on a finite space. Okay, so instead of the infinite line, or let's say random walk on the finite space. Yeah. This doesn't matter, right? I mean, no. I mean, because I'm just defining a Fourier transform. I mean, I can take plus minus anything. Okay, so we have some lattice 1 to L, and then we wrote this equation P of xt. Okay, and then we said that this equation, you can also write it in kind of matrix form where it's and so here, of course, the one has to be careful about the first row and the last row, because at the first row, there's no left neighbor, and at the last side, there's no right neighbor. Right? So what is the first term? Huh? So what's the first term here? Lambda r with the minus sign, right? So because this basically represents things going out of, so minus lambda r times p1 is a loss term. So diagonal loss terms, and then this is lambda l, and then of course 0, 0. And then the next term is lambda r again, and minus lambda l plus lambda r, and then lambda l, and then and so on. And the last side, I think, is maybe minus lambda L, and this should be lambda R. Okay, so this is the basic equation. And then so this is of course, so formally you can write it as basically so this I said it's called a W matrix. Okay, and one property you can easily see is that the sums are 0. Okay, so so that is necessary because, I mean, if you look at it, if you write this equation WT, so in component form this is PI. Right, so this is the matrix form, and so if I sum over all I, then I get del T sum over PI equals to, okay, so there's a, okay, yeah, yeah. Okay. This is okay, right? It's fine, okay. Well, thanks. Okay, so here I'm trying to prove that why this in general for any such equations the sum of the columns should be 0. Okay, so that's just a requirement of conservation of probability. So means conservation of probability means that so these are the probability that since it's in state 1, probability it's in states 2 and so on. So the sum is of course 1 and it should remain 1 under the dynamics, right? So therefore this should be what? This should be 0, right? Because this is always 1 at all times. So this left hand side, when I sum over all I, it should be 0. So for any choice of this piece, okay. So for any choice of piece, this object should be 0, which means that this sum has to be basically equal to 0. Okay. So because for arbitrary like whatever piece I put, as long as it was initially normalized, this thing is always 0 for any j. So this therefore this sum has to be 0, and this sum is basically means summing over columns of this matrix. Okay, and so this Wji is basically, if you it's basically probability rate of transition. Okay, so you should be careful about the which component, like it's not transition from I to J, it's J to I, right? That's important. Okay, so basically it says that probability of, I mean, rate of transition from J to everywhere, I mean, is 0. So you can write it in a slightly different way. You can also write it as Wij. So this is sum over J not equal to I. So I not equal to J plus, and so this okay, so basically this says that the diagonal element is equal to sum of all the other elements, right? So that's I mean, so these are the diagonal elements, and this diagonal element is basically what is going out, and all the things are coming in at a given site, right? So that's just sum is 0. Okay, so okay, and so now we want to try to understand how to solve this kind of systems in a, like when I have a finite lattice, okay. So we solved the case where on the infinite line, but now we want to solve this on the, okay, so what is a good way to solve this equation? Like some equation like this. Diagonalize the matrix W, okay, that's one way. Okay, so we diagonalize this matrix W, right? So which means trying to find some matrix U such that U inverse is equal to some diagonal matrix. Okay, so let's call it D. Okay, so this, of course, this W is not a symmetric matrix, right? That's one property. It can have, so it can have complex eigenvalues and so on. So it's not Hermitian and all that. So it's a real matrix, but it's not symmetric in general, right? So you may not be able to diagonalize it by orthogonal transformation, but you can always find some similarity transformation which diagonalizes it. So this is true. So then, of course, you can do a what is that? No, but huh? Okay, that's a numerical. Maybe you're talking of numerical scheme, right? Yeah, but we want to solve it analytically. Okay, so which means basically you have to find the eigen functions of this object, right? And basically both the right and left eigenvectors of this matrix. Okay, so okay, so let me let me discuss this in first by looking at this equation. Okay, so so basically we are saying that we want to so we have to find the eigenfunctions and eigenvalues, and then probably what we can do is do something like right. So okay, so when we diagonalize this matrix, we have to find the eigenvectors. So basically, that's the eigen function equation, right? So we have to solve this. So this is a matrix, and this is some eigenvector, and we have to solve this. And then, of course, we can see that the solution. So P of T. Okay, so basically, I'm saying that you can expand in this eigenbasis, and the time dependence will basically be this. So this is, I hope, is it clear that the solution can be written like this? It's like, okay, so actually this is very similar to quantum mechanics, right? So in quantum mechanics, you have, so in general, like there's I, but otherwise the equation looks very similar. So this is the equation for the wave function, and then we say that usually you can write a solution by finding some basis. So this is the general solution in the quantum case, right? So the structure of the equation is almost exactly the same as the for a quantum system, and so we can write a solution like that. Okay. And so here, how do we find this coefficients AQ? Right, yeah. So we have to know the state at time 0. And in this case, you just say that xi AQ is equal to IQ psi at time 0. Okay, so find the initial overlap, and then you prove, and then you have the complete solution, right? So actually on the real space, what we were doing is basically there we knew the eigenfunctions. Okay, so there the basis states are basically plane waves like e to the power iqx. So there we were basically finding the eigens. Okay, and now in a finite domain you have to find the eigenstates of this operator, and so we have to find the eigenstates of basically this operator. Right, and then we can do this method, right? So we can't do Fourier transforms or Fourier series because those are not good basis states, right? So we have to find the appropriate basis states. So this equation now, let's write it explicitly given this matrix W. So of course, by hand, if you try to diagonalize this, it's a bit difficult. So we have to basically write it in explicitly, the eigenfunction equations. Okay. So given the operator W, you can easily check that this will look like, the equation will look like lambda L Okay, so is this equation clear? Right, so basically I'm taking this matrix and writing the phi and equals to d phi. And then I'm just writing the each, okay, so basically it's, I mean, instead of p I have a phi here, and instead of del t I have a, the eigenvalue. Right, so it's, okay, so, okay, so I have to solve this equation, and how many eigenfunctions will I get? I'll get, if it's a L cross L matrix, I'll get L eigenfunctions, right? So somehow I have to solve this equation and get L solutions for different Qs. Okay. Okay, so now this equation I have to solve I have to specify boundary conditions because I know at the boundary there's some problem. Okay, so so what I said yesterday was the appropriate boundary condition is so I have a problem at site x equal to 1. So at x equal to 1, what I get some. So from here I get what I get is basically minus lambda r p1 and plus lambda L P2, right? But from this equation, if I put x equal to 1, okay, so if I put x equal to 1, I get this term I get, and then this term is not there. So this is an extra term, which is lambda R P0T. And from here, I get this term is there, and then I get one extra term minus lambda L P1T. Okay. So what I should do is I should, what I said yesterday was that I should set this to 0. Okay. If I impose this condition, then this equation is automatically identical to what I want. Right? So therefore I impose this condition, and similarly out here I have to impose another condition. So which means that this my wave functions have to satisfy the condition that lambda r phi 0. So here this wave functions have no time, right? The time dependence has gone out here. So 0 is equal to lambda L 1. And at the other end, I will have lambda L Okay, so so these are the two boundary conditions. Okay. Yeah, so so I just introduce some two extra sites, and then I say that this the weight at that site I set. I mean, it's almost related to the weight at 1. Okay, and the weight at L plus 1 is the weight at this. Okay, afterwards when I calculate anything, I'll be only looking at the sites in the lattice, like 1 to L. But this I just put as a boundary condition. So there's a so there's a theorem which we'll discuss later, called Perron-Froben theorem, which says that this kind of a matrix, if it's like the element, there are some requirements. The element should be positive and the sum should be 0 and all that. Then you can prove that all eigenvalues, the real part will be negative. Okay, so that's Perron-Froben theorem. Okay, so right. So now, okay. So let me just also explain, like physically, what does this mean? This thing. So basically, here, and what's happening is this is like it's like I have a random walk in a box with some reflecting boundary conditions, right? So you can imagine that every time this thing comes back, it kind of gets reflected back, right? So if you imagine there's a site at 0, it's basically what it's doing is that with some probability it's going to this site, that's lambda L times P1, that's the probability of, if I'm there, what's the probability of going? And then this probability at 0 is such that it gets reflected back immediately. Okay, so it's basically imposing reflecting boundary conditions. Okay, so now let's see if we'll try to see how to we'll explicitly solve this boundary condition. Okay, I think till here. Right, yeah, I'll just discuss that. Okay, so okay, so let's again go to a simpler case. Okay, so let's not put a bias. Okay, so in that case, this equation is just lambda and this boundary condition becomes phi 0. Okay, so now if you kind of stare at it and ask what is it in the continuum limit, right? If I go to the continuum limit, so then what is this thing? It's del square, right? So in the continuum limit, this corresponds to saying d del x square phi equals to d of phi. Actually, if you don't mind, I'll change this d to e. We haven't used e anywhere, right? E. Okay, so let's call it e. Okay. Yeah. So this is, let's say, and what does this become in the continuum limit? Derivative, right? So it's basically del x at phi at x equal to 0 is 0, and del x phi at x equal to L is 0. Right, so this is what you are saying, right? So in the continuum limit, it's exactly, so del x phi for the diffusion equation is the current, right? So basically you are saying the current at 0 and the current at L both vanish. So that's the boundary condition. Okay. So of course in this case, it's easy to solve this problem, like what are the eigen, so what are the eigenstates in this case? In the continuous case? Which satisfy these boundary conditions. Someone said sine. Is that right? So sine, of course, like when you take derivative, it's not 0, right? So obviously cos. I mean, if it's so, it has to be probably cos qx with some normalization. Okay, so this we see, of course, it satisfies this equation. And you also get EQ is basically EQ is minus dq square. And okay, so this, if you take derivative, so if you take del x, phi is sine qx. And if you put x equal to 0, that's fine. At x equal to L, of course, it's not 0, right? So you need both this and this condition. So one condition is satisfied. At x equal to 0, it's 0. And x equal to L, to make it 0, what do you have to do? Huh? Q has to be, Q will get quantized, right? So you have to say that QL is equal to n pi. So basically, in that case, Q is n pi by L. N goes from, okay, in this case, n goes from 0 to infinity. Okay, so this is, so if you have a box in the continuous limits, these are the eigenstates, and then you can, so if you want to solve this problem with, yeah, so this is in the continuous limit. But let's go back to the discrete case and try to solve it there. Yeah, so let's see what is the solution in the discrete. No, so see, we have gone to the continuous limit. This I was solving in the continuum limit. It's now, I mean, out here, there was a lattice of 1 to L. But when I go to the continuous, okay, so here, of course, L means the size of the box. It's no longer the number of lattice points. The number of lattice points has gone to infinite now, right? When I go to the continuum limit. No, it's not infinite. It's like you still have it's I mean, so you're solving the diffusion equation in a box. Okay, space is continuous, which means you have broken up between infinite number of points, but it's a finite box, right? So it will be completely different, right, from the diffusion equation. Okay, so even without going through the mathematics, it's clear. See, this now what is the problem we are solving? We have a box, and initially we start a particle, maybe which again is like a delta function, and then we want to see how it spreads, right? So earlier we saw it spreads like a Gaussian, right? Now, of course, at some point it will hit the wall. So if you look at short times, it spreads, but at some time it will hit the wall. And then eventually what will happen? At very large times, it will just be like if you have ink in a box, it will just be uniform distribution, right? So it will go to a, so this will be the long time steady state, a uniform distribution. So it's different from the solution in the infinite line where it keeps spreading forever. So here, of course, it can't go beyond this. Okay. Is D? Yeah, right. D will be, yeah, so lambda, and then there's, if we go to the continuum limit, there's some A square factor, right? So this is, if you go to the continuum limit, whatever you get. So D is probably, I think, lambda times A square, right? So because it has to have like dimensions of length squared by time, right? So that's D. Any other questions? Okay, so now we want to solve this equation. Okay, so anyone has an idea of like how I would solve an equation like this? So on the infinite line, we know solutions, right? So on the infinite line, what is the solution of this equation? If I didn't have any boundary conditions, then what is the solution? Huh? I mean, it's like a discrete Laplacian. So what is the solution? See, this is a linear equation, right? So, right, yeah. So this is a solution, phi qx equals to e to the power I qx. Okay, so now you can see that this solution is still, and also you can write another solution, maybe e to the minus iqx, okay. And you can see that this solution basically, or you can also the other, you can check that this is also a solution, sin qx, obviously, you can take linear combinations, they are still solution, right? So these are of course solutions. And this is satisfied, these equations, you can check this, that the equations actually satisfy the equation, so that's clear. Where EQ is what? So if you put phi qx equal to any of this into this equation, you'll get a expression for EQ. So which is? So if you put, let's say, e to the power iqx, you get e to the power iqq from here, e to the power minus iq from here, and minus 2. So that's minus 2 lambda 1 minus cos q. Right, so, okay, so these are solutions in the bulk, at least for x in the bulk, right? Then we have to impose the boundary conditions. So then what do we do? So this is like solving like particle in a box, right? There you have two solutions, sin qx, cos qx, and then you just take a linear combination and then try to match the boundaries. So you do exactly the same in this discrete box. You take a general solution like a sin qx, plus b cos qx. So this is a trial solution. This obviously satisfies this equation everywhere except the boundaries where you have to put these conditions, right? So basically, okay, so from this first equation you get, so if you put x equal to 0, this gives b equals to a sin q plus b cos q, and then the next equation is a sin q plus okay, and then from this equation you have to solve for a and b, and then you also find an equation which determines q. Okay, so this I won't go through the details, but if you finally if you solve all this, okay, so this gives the ratio b by a, and also it gives you kind of okay, so so I won't go through but the final solution that you get is basically phi qx is equal to, so what was that, was cos qx. So, so there are two sets of, so one solution there is a phi 0x, which is just 1 by L everywhere at all sites. Okay, so that's one of the eigenfunctions. And the other set of eigenfunctions are given by phi qx equals to this minus this, sine minus this. So this actually you can see, like if you go to the continuum limit, you get cos qx, right? So it's something which it's kind of what you expect to get in the when you discretize space. Okay, so so you can verify that this is the solution, but you can just follow the steps and get this also. And so A is some normalization constant which it's up to you to fix how you want to fix it. And Q is given by S pi by L, where S goes from 1 to L minus 1. Okay, so now this is a finite, so it's a finite system. You have to have a finite set of eigenfunctions. Which two sets? No, see, this two sets means there's just one function out here. It's just one function, and this is here. Okay, and yeah, so Q is this are allowed. So total number of eigenfunctions is L. Okay, any questions? Okay, so now let's do a really explicit, simple example. So maybe yesterday I was writing some six sides, but let's just take 2 sides. Okay, so even that's good enough to look at this problem. So let's say L is 2. Okay, and let's do this procedure, but also we'll try to do the things by hand. Okay, more directly. So here the equation is basically del T E1 P2. So there's just 2 sides or 2 states. Okay, so in fact this you can also think of like a spin system which can be in 2 states, right? If it's the particle is here, it means the spin is in down state, and up particle is here means it's up state. Okay, so and this is the probabilities of being in up and down, and then we are saying this has a equation like R minus lambda lambda. Okay, so now from here, what do we get? Okay, so we get, of course, 2 eigenfunctions, which are, so there's one function phi 0, which is just 1 by 2, right, at all values of x. So this vector will be 1 by 2, 1 by 2. And the corresponding eigen value is like if I put q equal to 0, so that's 0. So E0 is equal to 0. This is one of the eigenfunctions that I get from here. And the other eigenfunction phi 1 is, if I, so Q is, so S, L is 2 and S can only take 1, right? So that means Q is pi by 2. So I put pi by 2 here, and if X is 1, then this becomes 0. So I get sine pi by 2, which is 1, right? So, so there's some normalization. Let's take it to be 1. So the first t is 1, and if I put x equal to 2, then this becomes sine pi, which is 0, and this is minus sine pi by 2, which is minus 1. So at the second side, the weight is minus 1. So this is the second eigenfunction, and the eigenvalue E1 is equal to, so Q is pi by 2, so this is 0, so that's minus 2 lambda. Okay, so now of course you can verify that this is correct, right? Given this matrix, it has 2 eigenfunctions which are either 1, 1 or 1 minus 1, and then these are the correct eigenvalues, right? Minus, yeah. Okay, so I hope this is clear, right? Okay, and okay, and then we, okay, so then we said that, okay, so this is what we were calling the W matrix. And so now if you want to diagonalize this matrix, U inverse WU equals to E. So what is this? U is given by, so if we have found the eigenfunctions of this W matrix, then we can immediately write the matrix which diagonalizes W, right? So what is the matrix? So it's basically half, half, and 1 minus 1. And then if you take U inverse, you can check that it is 1, 1, half minus half. Okay, so I think it's 1, 1. Yeah, it's right. Okay, so this is the U inverse. Okay, so which means that if you know U inverse, basically it means that you know the left eigenvectors. Okay, so in this case, the left eigenvectors is chi0 is 1. So left eigenvectors are basically the rows of this U inverse matrix. So chi0 is 1, 1, and chi1 is half minus half. And A0 is equal to right. This is the general solution of time t. So let's say we can start from any initial state. So so let's consider P0 is equal to, for example, you can start from the particle is in site 1. Okay, and then you want to see how the probability evolves. Okay, so if this is yeah, then if you so for this so this is initial condition. So A0 is what? If P0 is this, A0 is 1, right? If it's because chi0 is that 1 state, 1, and A1 is half. Okay, so therefore, finally we can write the explicit solution P1 time 2t. Okay, so so here are the two things to notice. So one is that if you look at time going to infinity, then of course this term goes and you go to this 1, right? So it is 1, right? Oh, sorry, half. So because P0 was no 1. Wait. P0 is 1, guys. What is 1.5? Oh, sorry. This was. Huh? No, what does anyone see? 50 is half. Oh, sorry. This is okay. You see, this 50 was half, right? So this half is okay. Right, this is fine. I mean, because A0 is 1, which is okay, and 50 I wrote as half, so that's fine. So this is of course normalized, yeah. Okay, so okay, yeah. So what I was saying is that T infinite it goes to this state. So which means okay. So initially I have these two lattice sites, and I start with one part like the particle is here. So the probability is 1 here and 0 here, and then at long times it basically becomes half, right? That's the steady state. Obviously, because it's a unbiased random walker, so it's just a half equal probability. And then you can ask, how does it relax to this state? What is the time it takes to go from here to here? So, so the relaxation time is given by 1/2 lambda, right? So that is equal to 1/2 lambda. Okay, and basically it's in general it will be the so you have to find the so it in general it's the sum of many exponentials, and at large times the largest kind of eigenvalue with the realest large. So it could be complex also in general. So you have to look at the real part, and inverse of that gives you the relaxation time. Okay. So the ground state, which is a 0 eigenvalue, corresponds to the steady state, and the first eigenstate gives you the relaxation to equilibrium. Okay, what was thinking of? Okay, so now here there's some, okay, so here one thing we see that is the sum is always 1, right? Somehow this term is became 0 at all times, like when I add these guys. So that's a general thing. So let's see now if I write our general solution, E T is equal to, so there's initial is A0, phi 0, and then plus Q not equal to 0, AQ e to the power EQ T IQ. Okay, so if you have a more number of sites or states, then this is the general solution. And in this case, okay, so one question is what is A0? So phi 0 is the, okay, so what is phi 0? So phi 0 is the, so here we saw that this is always a zero eigenvalue, right? Phi 0 is the state with 0 eigenvalue. So in this case, so in general, there's always a 0 eigenvalue. Okay, so the reason is that, so I wrote this W matrix, and we said that it always has this property that sum over I equals to 0, right? Which means that, basically it means that when I write this matrix, I can always construct a state which is like 1, 1, 1, 1, 1, such that this is equal to 0. Is that clear? This statement, these are equivalent, right? Because, so there's always a left eigenvector, which is all 1, 1, 1, and it gives you a 0, it's a 0 eigen, it's an eigenstate with 0 eigenvalue. Okay, so this kind of matrices which have this property that the column sum is 0 always have a solution where the eigenvalue is 0. Okay, and of course, if you have a left eigenvector like that, you also have a corresponding right eigenvector, and that will be the steady state. Okay, so here what I'm saying is that there's always exists a state such that chi 0 is equal to 0, which means there's always a state with such that phi 0 is equal to 0. Okay. And this is the steady state because we have del TW, this is the equation. And if I put P equal to phi 0, then of course this is 0, which means that the state doesn't evolve with time. Okay, so okay, so basically the 0 eigenvalue solution of this matrix corresponds to the steady state. Okay, and okay, so now, so one question is what is this A0? So A0 we said was equal to, so A0 was equal to I0 times the initial state, right? Okay, so now this is always equal to 1. Okay, so so can you see this? Huh? How, why? No, there's no infinite time. This is the state at times. This is my initial condition, and then I'm no, right, yeah, because this chi 0 is a vector with all 1, 1, 1, 1, 1, right? So therefore, when I take this, it's basically sum over Pi 0, and because the initial state was normalized, this is equal to 1. Right? So this A0 is always 1. Okay, so 1, and then I have this. Okay, so now the other question is that like at why does it stay normalized at all times? Okay, so if I want to find the normalization at a later time, then the normalization is basically, so the normalization at time t is basically chi 0 times pt, right? Because this basically gives me sum over pi. See, because this chi0 is always 1, 1, 1, 1, 1, 1, right? So this gives me sum over pi. So now if I take this chi0 dot product with this, so this gives me 1, chi0 phi 0, and chi0 phi q is what? Yeah, it's orthogonal basis, so these are all 0, right? So basically, which means that when I, for any of these eigenvectors, if I sum the columns, it's always 0. Okay, that you can see there for the two particle case, this is 0, right? 1 minus. So even for any system, if you take any eigenvectors, the sum of the columns will be 0. Okay, so okay, so this is the steady state, and is given by okay, so in general, you have large number of eigenvalues, but you have to find the kind of, okay, so the eigen spectrum is like, if you look at the real parts of these eigenfunctions, so there's a 0, and then these are like, they're all negative, the real parts. So that's a difficult, there's a theorem called Perron-Froben theorem. So I won't prove it, but I'll just state it. So okay, so this theorem basically ensures that you'll always have relaxation to the steady state. Okay. Now you can cook up simple examples where there's no relaxation, but that just means that there are some conditions that are not satisfied. But generically, if you have some like a typical physical system where you are writing this kind of rate equations, this will work. Okay, so what I was saying is that you have a 0 eigenvalue, and then you can arrange this in terms of their real eigenvalues. So this guy basically determines the relaxation to equilibrium, right? Because at large times, these guys will all, the contribution of all these other Qs will be very small. So the first one will tell you the relaxation time. And the time is basically given by 1 by, let's say, 3Q. So this is the relaxation time. Okay, any questions? So again, that theorem is for a finite lattice. If you have infinite, then you have to be careful and all that. Steady state. See, for example, like I said, it depends on the situation. Of course, like if you have diffusion on the infinite line, there's no steady state. It keeps relaxing. If you have diffusion on the finite box, even though it's infinite number of, like it's a continuum, right? In that sense, it's infinite, but it's a finite box. Then you still have equilibration, and you have a unique steady state. So, but there are if you have infinite lattice, let's say. Okay, then you have to worry about whether there's some problem with the theorem and all that. Yeah, any other questions? Okay, so the question that he was asking is basically like, okay, so right now we looked at some lattice and, okay, so we solved this two-side problem, but then in general, if you have n sides, you can explicitly, like we have explicit solution, right? So you can do, even for n sides, this problem you can do exactly. And one thing is like, we saw that there's a zero mode solution, which is 1 by L, and that corresponds, that obviously is the ground, a steady state, right? Because even if I have a long lattice, after a long time, it will all go to 1, 1, 1, 1. Okay, so now the question he's asking is like, right now we said that these rates are all lambda everywhere, right? Now, supposing you make them kind of random. Okay, so like depending on which site I'm, so lambda 1, lambda 2, and so on, then so you have to make sure that you still have yeah, conservation and all, but you can just put random rates at all sites, right? Left, right rates at every site is random. Okay, so then when you write this equation, the matrix, it will look like maybe, let's say, minus lambda 1, what, lambda 2, 0, 0. Okay, let's just, this has to be lambda 1, and this has to be lambda 3. So there's some constraints, right? I mean, it has to have some structure. Then you can put a random lambda 4 here, and okay, so you can put random lambdas, but there's some constant that the sum has to be 0 and so on. Okay, so here, of course, okay, so in this case, one thing that is still true is that you have a left eigenvector with 1, 1, 1, 1, 1, right? So now what is the right eigenvector? Is it still 1, 1, 1, like it was 1 by L in the previous case, right? Now it's not, probably not 1 by L. So it will be some, I mean, obviously if you have like, let's say from one side, there's a large rate of hopping out. Okay, and in some, there's a very small rate of hopping out. So then, of course, you expect that in the steady state, you will have some, the steady state distribution, like places where the probability of going out is very small, will probably have a large weight, and so you might get a, so the steady state might look something like that, okay. But now, okay, if you have, so that's the steady state. But what are the other eigenfunctions? What do they look like? Okay, so in this case, the eigenstates were like sine qx, cos qx. So they are kind of, basically they are like periodic solutions, right? With the various, maybe different periods. Different q gives you different periods, but they're kind of extended periodic solutions. Now, typically what happens is if you have a random matrix like that, then the eigenstates don't look like periodic objects. I mean, are not extended objects, but are localized objects. Okay, so they might look something like that. Okay, so you still have L eigenstates, but all of them look like, they don't look like plane waves, but they look like some localized object. Okay. So for in quantum systems, this makes a big difference to like then things get stuck and so on. Okay, so for a classical system, I don't think you get stuck. So right now I can't think of why exactly, but I think it's true that if you start from some point with random lambdas, you'll still diffuse out and equilibrate. Equilibrate means reach a steady state in some, it's not very slow diffusion. Okay, is any questions on this? Okay, please ask questions if anything is not clear, because otherwise, I mean, because it's not difficult really. I mean, okay, so I assume it's clear. Okay, so okay, so now basically what I wanted to say is that this kind of master equations is of course valid for general stochastic systems. So right now we had a system where so let's say in general, for example, if I take a spin system, okay, so if I take a single spin, then it can be in it can be in two states, right? Sigma is equal to plus minus 1. Right, and then I can ask for some dynamics which moves it between these two states. If I have two spins, let's say sigma 1, sigma 2, then there are four states, and so they can be in states 1, 1, 1 minus 1, and okay, so this one I can think of the two states like this, and here I have four states which I can think of maybe on a square. So this is 1, 1. So these are four states, and then I can ask like there's some dynamics maybe which there's some transition rates between these various states. Right, I can, so in general for any system, basically I have to identify how do I label configurations. So for a spin system, I would have to specify the spin configuration. For a random walk, it was just the position of the random walker. If I have if I have, let's say, this lattice problem, if I have, let's say, instead of one random walker, I could have two random walkers. I call them x1 and x2. So in this case, the configuration is described by the positions of the two walkers, right? So, so in this case, so this is the configuration for two spins is described by giving the sigma 1, sigma 2. Here, the configuration is given by x1, x2. And in the usual random walk case, the configuration was just given by specifying position of the walker. But basically, it's then in this Markov dynamics is corresponds to specifying like the transition rules for going from between different states. Right. So in general, if I have any system described by set of configurations, then the dynamics is given by del t. So this kind of master equations describing the dynamics is equal to WC prime. Okay, so whatever we discussed about the random walk is those properties will still be satisfied obviously by this matrix W, right? So I mean we can for example this will also satisfy this property WC. So this is true, and there's a left eigenvector, and then the solution is again given by some series like that. So all those things, it's completely, you can imagine just, if you just like the states you specify, then everything follows, right? So I hope that point is clear, right? Okay, so for example, this two-side problem we discussed is like writing the dynamics for a single spin in a, if you have done this Monte Carlo dynamics, there you specify transition rules between up and down states, and there you have a matrix like that. Okay, so for example, for the spin system, so how many of you have done like Monte Carlo dynamics? Can you raise your hands? Is that all? I mean, okay, so a lot of, okay, because that's it's okay. Yeah, I mean, I think everyone should do Monte Carlo simulations because that's. Yeah. So in Monte Carlo simulations, what you do is like if you have a single spin in a magnetic field, so you have a Hamiltonian which is minus h sigma, right? So if sigma is up, you have low energy. So this is a state with if the spin is let's say up, it's in low energy state. If it's down, it's in a high energy state. So this is the energy here, the energy here. Okay, and then the Monte Carlo basically says that with some rate you go from here to here, and with some rate you go from here to here, and then the only thing you specify is the ratio of these rates. Okay, and the ratio of the rate should be what? Huh? Yeah, it should be the e to the power the difference of energy, and then yeah. So basically, so this is, let's say, upstate to downstate, and then upstate downstate. So again, I can just call this rates. So probability of the rate at which you go from down to up is, let's say, lambda, and this is minus lambda, lambda minus lambda. Sorry, this can be different right now. So this is, let's say, lambda. Okay, so this is the rate of hopping from up to down or down to up. This one is rate of hopping from down to up or up to down. It's from down to up. Right, so this is down. So so this is lambda L, and this is lambda R. Okay, so instead of the like random walk, now I'm thinking of these two states, and either I can go down with some rate and go up with some rate, right? And then the only thing that I should specify is that this ratio lambda L by should be equal to e to the power minus beta difference in energies between these two states. So beta. So this is energy of the upstate minus energy of downstate. Okay, so let's see. Is this right? Okay. Okay, and now, so one thing you can check is that, so what is the steady state in this case? So how will we find the steady state? Huh? No, like the general prescription we have given so far, right? What is the method for finding steady state? The zero eigenstate, right? So we have to find the zero. So is there a zero eigenstate? So first of all, there has to be a zero eigenstate first of all, right? Without doing any calculation, we know immediately. Why? Because we know there's a zero left eigenvector, right? So there has to be a zero right eigenvector. So so in fact, we can just write lambda R, lambda L, and then just put some let's say this is the eigenfunction we're trying to find. So phi 0, 1, phi 0, 2. And this, of course, has to be 0, right? Because we know there's a 0 eigenvalue. So then we know the ratio of the states. So phi 0, 2 by phi 0, 1 is equal to, okay, so let's write the first row. So minus lambda R phi 0, 1 plus lambda L phi 0, 2 is equal to 0. So this means that phi 0, 2 by phi 0, 1 is equal to L. Right, yeah. Okay, so and then of course we can normalize and find the two values. Right? So this is the ratio, and from here we know that the ratio is, this is something we put in the dynamics, that this ratio is equal to this. So therefore, this is equal to e to the power minus beta e down minus e up. Okay, so this is the ratio between the states. So therefore, okay, and then so then what is the correct solution? So correct solution is e to the power minus 0 is which one? So this is 2 is down. Okay, so you can, so given that the ratio is this, and if you want to look for a normalized solution, then it's basically this, right? And you can check that this ratio is matches with this, okay? So basically we see that the steady state for this dynamics is what we expect the system to have, right? It should be the, it's the equilibrium distribution. Okay, so basically the Monte Carlo dynamics is chosen in such a way. So this is something which is called detailed balance condition. It's chosen in such a way that you are ensured that whatever state you start from, eventually it will relax to thermal equilibrium. Okay, and so this is another, you can see it explicitly. And then you can ask how long does your Monte Carlo dynamics take to converge to the steady state? And in that case, you have to find the first eigenvalue. Right, so so that again, of course, you have to find the solution. Okay, so this is, I'm just giving another example where like you do exactly the same kind of thing with this master equations. Yeah. Yeah. Why 1? No, this is, sorry, 0. Right, yeah. Okay, so, okay, so maybe what should I do now? Okay, so there's 3 minutes. So maybe I won't start anything new. There's one other point I wanted to mention is that you can also write this kind of. So we, let's say we didn't go to the continuous time limit. Okay, so supposing you are like the discrete time case. And there we had equations like, let's say for the random walk, we had an equation like px n plus 1 equals to some terms, right? Px plus 1 plus something. Okay, so here clearly we can also write, so here we can't write, obviously, the left-hand side is not del Tp. So here the evolution equation can also be written in matrix form. But okay, so this is a vector which is evolving in discrete time, right? So let's say I call it P, this vector P at time n plus 1. Okay, and now this is given by some matrix T times a vector at time n. Okay, so this, when you write in discrete time, it has a slightly different structure. This, yeah. So this matrix is, okay, it's again like a W matrix, but for discrete processes, it's sometimes called a Markov matrix or a stochastic matrix. And here there are some small differences in the properties. which I just wanted to mention. Okay, so if you write it in, let's say, a component form, then it's like pi n plus 1. So this I, now you can think of it as like in configuration space, right? So each configuration is specified by some index I. So it need not be a random walk, any Markov process. So pi n plus 1 is Tij Pjn. Okay, so and this gives you now. So earlier it was transition rates, and now it is transition probability, right? So probability of okay, and now here what you see is that if you sum over pi. So this is what sum over pi at any time, it's 1, right? So if you take this equation and sum over I, so then you get equals to 1 equals to sum over Pij Pj, and there's a sum over j and there's a sum over I. Okay, so now therefore, like earlier we had this condition Wij sum over I is 0. So now what will we get? So what is the condition? Tij sum over I, clearly it has to be 1, right? This, okay, so if you are writing this matrix in discrete time, then this matrix has a different property, right? Sum has to be 1 instead of 0. And okay, so for the random walk, like when you write this matrix, let's say on a supposing you have just or even let's say 2 sides, if you write a random walk on these 2 sides, then the equation, let's say completely unbiased random walk. So what is the matrix T? It's clearly half, 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 half. Okay, so okay, maybe it's better to write 3 sides. Okay, let's say it's on a ring. Okay, maybe otherwise it's confusing. Supposing you have 3 sides, and you are each time you can hop with probability half, half, half. Okay, so then this matrix will look like, okay, so there's no probability of staying where you are. There's a probability of going to the this side or this side. Okay, so and then you have half, 0, half, and then 0. Okay, so this is the matrix T corresponding to a random walk on a ring with 3 sides. Right? So I hope this is clear, right? So in this case, it's different from the continuous case where these diagonals were all negative things. Here, I mean, now the sums are 1. And you can see that there's a left eigenvector with 1, 1, 1, 1, 1, which gives an eigenvalue 1, right? So it's 1. So you, in this case, in the discrete case, you have left eigenvector with the eigenvalue 1. So, and that's the steady state, right? That's clear because in the steady state corresponds to this P doesn't evolve in time. So steady state condition is TPSS is equal to PSS, right? Because P is not evolving in time. So therefore, this is the eigenfunction of T with eigenvalue 1. So in the discrete case, it's slightly different. Okay. But yeah, then instead of like, you can similarly do a diagonalization, and otherwise it's very similar. So maybe we'll stop here.